Another thing that's pretty popular is to create a system where one mass is sitting on a frictionless surface and another mass is tied to it and hanging off the edge. So this will be mass 1 and this will be mass 2. And this one, we can do the same thing as we did before. We can find out what the acceleration is, and we can find out what the tension is. And this one really lends itself to the system trick. Oh, by the way, this one, there's no chance that it's going to accelerate back this way because there's nothing pulling it that way. So the wise choice of coordinate system is mass 2 falling, dragging mass 1 with it. And we'll see that the acceleration of this system is less than g, because although mass 2 is just hanging here, he has to bring along with him this other guy. There's more inertia because there's two masses. If we use the system trick, then we treat this object like a compound object, and the only force pulling on this object is the weight of mass 2. No friction, so nothing pulling back the other way. Hey, next chapter, there will be friction. And the mass of this object is m1 plus m2. So we can really easily figure this out. This is the setup. I'm going to go over here to start my math because I want to solve for A here and I want to solve for T here. So here we go. Um, F net equals m times A. This is training wheels. You can kick it off and not use it if you want. The next step is where we do our heavy lifting. M2G, that's the net force because there's only one, equals quantity M1 plus M2 times A. And we get that A equals M2, M1 plus M2 times G. And this is a ratio that will always be less than 1 because it's got M2 on the top and then M2 plus something on the bottom. The bottom's always going to be bigger than the top. We can then substitute that in, and we have to draw a free body diagram for one of the masses. Let's do it for the hanging mass. That's probably the more exciting one. Oh, I don't know. Well, let's have some fun. Let's do it for the other one. There we go. So T is the only force on M1. I agree. Look, folks, there are some up and down forces, but they're canceling each other out. I'm ignoring them, all right? So then the F net equals M times A becomes T equals M1 times A. But A over here is this thing, so we'll substitute it in. So we're going to have M1 times M2 over M1 plus M2 and times G. And that's the tension in the string. And that's a different system. Now, we can make this a little harder if we do the next higher level of problem. And again, I'm working with no numbers here. These are general results, okay? Some people find this really elegant and neat, and those people become theoretical physicists. Here's a problem that sometimes drives students to distraction. And this one has a inclined plane at the top of which is a pulley. And so we have a mass on the inclined plane, inclined at an angle theta. A rope goes over and a mass hangs here. This again will be mass 1 and this will be mass 2. And now the system trick, and you don't have to use the system trick, you can draw two free body diagrams, is a little more complicated because we have to invoke our inclined plane knowledge. And so pulling this way is the hanging mass, m2 times g, hanging weight, I should say. And pulling the other way is some fraction of m1 because he's no longer on a horizontal surface. So there's some part of his weight that's going to be pulling down this way. And if you remember your inclined plane stuff, you'll realize that it's m1g times the sine of theta. The sine is the function that pulls it back down along the plane. The cosine was the part that holds it on the plane. And of course, our combined mass is m1 plus m2. So, solving for the acceleration, we will say that F net equals m times a. The F net in this case, and I'm going to take this to be positive. That means this is positive direction. That means we put m2g first, and we subtract away m1g sine theta, and that's going to equal the combined mass m1 plus m2 times a. Remember, F equals m times a. For a compound object, you have to use the total mass. And let's see what we can do here. Factoring out the g, we have m2 minus m1 sine theta, and then we'll bring this underneath. It's times g. Bring that underneath, m1 plus m2, and that's going to be a. So this is our acceleration. It's a little less than the one for the horizontal surface because there is some force retarding or pulling backwards, and that's this term right here, the one associated with m1 and the sine of theta. Then we draw ourselves a quick free body diagram, and in this case I think the hanging mass is clearly the one that is easier to handle, m2g, and we'll write F net equals m times a. And in this case, downwards is positive, so F net is m2g minus t equals, and now we need the combined mass times a. Ooh, and a is huge and ugly and ugh. Okay, let's give it a shot here. So we're going to go m2g minus t equals the quantity m1 plus m2 times, and there's going to be a g over here, and up here on top is m2 minus m1 sine theta, and on the bottom m1 plus m2. Oh, hey, that's not bad. Look at the cancellation we get here. So we're going to have m2g minus t equaling, now these two cancel, so all that's left is m2 minus m1 sine theta times g. Okay, we need to isolate t, so we're going to move him to the other side. It'll be a positive t. We're going to bring this to this side, so it's going to be m2 minus the quantity m2 minus m1 sine theta times g. Ooh, all of it times g. Check it out. There's a g here and there's a g there. So all of this times g equals t. Well, m2 minus m2 is nothing, and minus of a minus of m1 sine theta is something. So we got m1 sine theta quantity times g equals t. Wow, that was somehow easier than the other one. Interesting. So that's a very complicated system, and you can see how the system trick kind of helps you along with these things.